So we're supposed to have a quiz today. I entered the quiz on D2L and gave you all 5s. So we won't do that. We have a pretty good amount of stuff to get through in the next couple days. The lab this week is just the post-test of that intuition bubble sheet test. Taking it won't affect your grade, but if you take it, I'll give you a point back on one of your exams. So that's good. It's worth coming. All right, and then the last exam, you have a choice of Monday night at 6 p.m. or Thursday night is the day class, 2 p.m. In this class. Okay, so Monday or Thursday of finals week.
Monday is in this class?
Monday is that way, next door, 1326. Okay, so today we're going to start talking about rotational motion. Up until now, everything we've talked about has been particle physics. So, can anyone remember what the things are that make something a particle analysis? That's right. Yep. So, particles meaning we don't care about the orientation. And as a result of that, there's something else. It has no length dimensions, and the way I was going to say it here, yep, that's exactly right, is it doesn't matter where forces are applied because we're assuming all forces act at the same point. You know, there's no distinction between this side and this side. So no length dimensions. Well, that was supposed to be number 2. So now both of these with rotational motion, these change. Now we are concerned, we do care about an object's orientation. And where on the body forces are applied does matter. And there are 2 things that you should look for as we go through this stuff. These are things that I think will help you sort of store this rotational physics in your head. One is that rotational motion and circular motion are very closely related. They're not the same thing. So there's a close relationship between rotational motion and circular motion. So first, let me just kind of describe the distinction between these 2 things. So circular motion is I need to find a good spot. Okay, this is circular motion. Da, 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 da. You know, it doesn't. My orientation doesn't matter. I can be doing all this stuff. What matters is that my feet are moving in a circle. Okay, that's circular motion. That's what we've done. The new thing is rotational motion, and that's this. Okay, so no. So rotational motion is the orientation changing. Circular motion is the location changing. Okay? And the second thing to look for is there are analogous quantities and equations for almost every equation that we've used, quantity and equation that we've used in particle motion. So let me say it like this. Every rotational quantity and equation that we'll use has an analogous particle quantity or equation. And so, in a way, you won't have to remember all this stuff new if you do a good job of just thinking like, okay, that's the rotational version of this thing that, you know, that's the rotational version of velocity, that's the rotational version of acceleration, that's the rotational version of Newton's second law. All of these things are going to have forms that we've seen before, even though they'll stand for something a little different. We're going to break rotational motion up into two parts, just like we did with particle motion. So rotational motion will be broken into rotational kinematics, this is just a description of the rotational motion, stuff that you could calculate purely from looking at a video. So this deals with quantities you could measure from a video. And then after that, we'll talk about rotational kinetics. That combines kinematics with causes of the motion. And the flow of the way that I'll talk about this stuff is going to really closely follow the flow of how I talked about particles. So all of this should look a little familiar, but it's going to all stand for slightly different stuff. It's all going to stand for descriptions of the way that rotation and orientation of an object is changing. Okay, so we'll start with rotational kinematics. Okay, so I want to first start by these two things that I said to notice, let's see, two things to look for. I said we're going to see a close relationship between rotational motion and circular motion, and I said that all these rotational quantities are going to be related to things we've seen before. So I want to talk about those first. First, the relationship between circular motion and rotational motion. Okay, so imagine you have a rectangular board, and let's say it's attached to the wall by a big bolt. And so this board can spin around. The point that's connected to the bolt can't move, but this thing can spin around like this. You know, if I took it and threw it down like that, it would spin. Can you picture that? So this bolt is the axis of rotation. So in a way, all that this body is doing is changing its orientation, right? But think about what points, material points on the body do. Like let's say there was with a marker you drew a dot here and you drew a dot here. What are the paths of those 2 points on the board? This one follows a circular path like this. That's supposed to be a circle. And this one follows a circular path with the same center, but a bigger radius. So when an object changes its orientation, or when an object rotates, material points move in circular paths and the center of those circular paths is the axis of rotation. And so if we wanted to, we'll do a lot of stuff about measuring the change in orientation of something like this board. But then if you wanted to go from the calculations involving the change in orientation to calculating, like, say, the accelerations of these points, which is something that is useful pretty often, then you would have to figure out what the velocities are of those points. You'd have to think about the centripetal acceleration, the tangential acceleration, add those two together. And so we're going to be going back and forth a lot between descriptions of the rotation and then using the descriptions of the rotation to calculate accelerations. Yep?
But won't the acceleration will be the same since it's attached to the kind of like the bolt?
It's not, actually. If you put a bug on this bolt, well, if you put him on the bolt, he wouldn't move. So let's put him next to the bolt. He'd be spinning around with he'd have a very small acceleration and a very small velocity. If you put this bug out here, he'd have a big acceleration and a big velocity.
Because it's traveling more in the same amount.
Yeah, right. That's right. That's a good way to think of it. He has to go a lot bigger distance in the same amount of time.
Too big.
Yeah. So that's something, I'll bring it up again, but what we're going to see is that these rotational quantities that we're going to talk about represent an entire body, okay? The translational quantities, acceleration, velocity of these points, those vary from point to point. Okay, so you can't talk about like the velocity or acceleration of the whole thing. But rotationally speaking, you can do something like that. All right. So now that's the relationship between circular motion and rotational motion. So now let's think about these rotational versus particle analogies. What quantities sort of have the same function? What equations sort of have the same function? So over here is particle. Over here is rotation. And when we first started talking about particle kinematics, we started with position. The rotational version of the position vector it'll be denoted theta, and it's going to be called the angular position. And just like this one tells you an object's location at an instant, this one tells you the object's orientation at an instant. And then after position, we define the velocity vector. And for rotational motion, the version of that is the Greek letter omega, and that's called the angular velocity. And then the third one for particle kinematics was acceleration. And there's also an angular acceleration. We'll call it the Greek letter alpha. And we're going to see when I start going through the definitions that the relationship between theta and omega is the same as the relationship between P and V. Same with omega and alpha, V and A. All these relationships are going to look really familiar. Okay, so those are all the quantities that make up kinematics. And then after that, for particle motion, we went on to particle kinetics. We started by defining the mass. And the mass was a resistance to an object's acceleration. There's a rotational version of mass also called the mass moment of inertia. I'll always denote it capital I sub A. It's the mass moment of inertia. And it's a measure of how easy or hard it is to get an object spinning. Just like this is a measure of basically how hard it is to get an object moving. And then in order to overcome the inertia of an object's mass, to get it accelerating, you need to apply a force. So the next kinetic quantity I defined was force. And the rotational version of force I'll call m sub a, and that people either call that moment or torque. Either one of those is fine. But like a torque wrench, that's exactly what it's measuring. You can think of it as It's not a force exactly, but it's something like a force that measures how much effort you're putting into getting something turning, getting its orientation changing. And then the final result from kinetics was Newton's second law. It says add up all the forces. That's equal to the mass of the object times its acceleration. In rotational motion, just put in the analogous quantity in every spot, and you get that ma is equal to the mass moment of inertia times the angular acceleration. See, every quantity in this equation is right where Newton's second law suggests it should be. I don't know, I'll call that the rotational or angular Newton's second law, but that's our main equation of motion for rotational motion. All right, so now what I'm going to do is just one by one, the same way I did with particles. I'm going to define angular position, angular velocity, just go down the list. We're going to work our way through some kinematic calculations, and then when we're done with that, maybe that's probably about all we'll get to today. And when we're done with that, we'll go on to kinetics.
So M and F equals MA, those are kinetics.
Yes, these are kinetics. That's right. So, yep.
I'm sorry, what's the difference between kinetics and kinematics again? Oh, wait.
Kinematics is, think of kinematics as stuff you can measure just from a videotape, and kinetics, so how fast is it going, how much is it accelerating, what's its position at this instant, and then kinetics combines that with information like the mass and the forces applied,
Okay.
which are the causes of the motion.
Okay, so kinematics is basically like what you can see.
Right.
Versus,
Yes.
okay,
That's right, exactly.
thank you.
Yep. And kinetics sort of combines that with what you can feel.
Okay.
Okay, so I'm going to start with angular position. So angular position is an angle that gives the object's orientation at any instant. The units are radians. We've always done our angles in degrees up until now, but these are all going to be given in radians. You don't have to change your calculators because we're not going to use sine and cosine with these. So for this whole class, you can keep your calculators in degrees. But to convert from degrees to radians, you can use the fact that pi radians is equal to 180 degrees. So, for example, 60 degrees to do this conversion. Multiply that by pi radians over 180 degrees. the degrees cancel, and you end up with pi over 3 radians, or 0.3 repeating times pi. To measure a body's angular position, you have to choose a reference vector that's fixed on the body. It just has a slash. It's degrees, and then I canceled them.
Oh.
So choose a reference vector fixed on the body. And then measure the counterclockwise angle from the reference position to the current position. Okay, so let's say we're talking about the change in orientation of a car. You can choose your reference vector however you want, but I'll choose it like this. You can imagine just spray painting that on the car. You know, do it with someone else's car. And then after some amount of time, let's say the car is in this orientation. Do that with someone else's car too. Okay, so the spray painted arrow is going to look like that. And to measure that angle, put those tail to tail. And then the angle is from this starting position to this. That's your theta. And that's equal to, let's say that's 110 degrees. But we want it in radians, so we have to do that conversion. So 110 degrees times pi radians divided by 180 degrees gives you and then, yeah, times pi, right? Which, and if you multiply 0.61 times pi, you get something like 1.92. So that's the angular position of the car in that second picture. One thing to notice about not just angular position, but actually all of the angular quantities is that as an object rotates, all of the particle quantities are different for each point on the body. So let me show how that works. So the particle quantities are different at each point on the body. But the rotational quantities represent the entire body. Okay, so if you think about this car, this car now has some length. So the position here is different than the position here. Same thing here. The position here is different than the position here. And as it's rotating, there's some point on the body where the velocity is 0. That's whatever its axis of rotation is. Other points have a big velocity, and that's true of acceleration too. But the angular position we calculated for the entire object. We spray painted one arrow on that car, and the orientation of that arrow told us the orientation of the car. And that's going to be true for angular velocity and angular acceleration too. Okay. So angular quantities represent the whole body. Those particle quantities represent just a single point on the body. Any other questions yet about angular position?
How did you know this was 110 degrees?
Oh, I just looked at it. It looked like about that. Yeah. I mean, you could measure it with a protractor or something.
Will probably be given.
You'll be given it. That's right. Yep. But like on a videotape, I said kinematic stuff you can always tell from a videotape. You could take a protractor up to the screen, measure it that way.
Okay. I do have another question.
Mm-hmm.
So, when you said you put them tail to tail. Oh, just kidding. I
Okay.
answered my question.
Yes, sure. What does what come from? Oh, that is just an identity. That's just, you can think of that as the conversion factor. It's the same as yes, that's always what you'll use to convert from degrees to radians. Okay, so now we're going to use the idea of angular position to define angular velocity. So before I do this for rotational quantities, remember how we defined velocity based on position before. We first defined an average velocity that was equal to the position at a later instant minus the position at an earlier instant divided by the elapsed time. And then, the average velocity wasn't really the one we wanted. We really wanted instantaneous velocity. And so we defined instantaneous velocity as being, I'm saying this is approximately equal to, the way we thought about it was we kept pinching these closer and closer together and kept taking average velocities, and the value that you approached as you pinched them closer and closer together was the instantaneous velocity. So I'll say the instantaneous velocity is about equal to the position at the later instant minus the position at the earlier instant divided by the elapsed time for two instants that are close together.
Is that because the average velocity isn't going to change very much in two instances that are close together? And so it's kind of just like...
That's right. Yep, that's a good way to think about it. Yep. And so the velocity vector measured how quickly the position was changing. And so we're going to use a similar definition for angular velocity. So similarly, you can think of average angular acceleration as being equal to, not Q, the angular position at the later instant minus the angular position at the earlier instant divided by the elapsed time. And then use that idea to think of a process of just pinching those two instants closer and closer together and seeing what you approach for the instantaneous angular velocity. So the instantaneous angular velocity, again, it's the one that we care about, is approximated by theta 2, theta at the later instant, minus theta at the earlier, divided by the elapsed time for T1 and T2 close together. And so just like velocity measures how quickly the position is changing, angular velocity measures how quickly the orientation is changing.
Could you briefly explain the difference between position and orientation?
Yeah, well, the position, let me pull up that car picture. So to measure the position, you choose a coordinate system, and then in that coordinate system, you just have some point that you're trying to track the position of. Let's say that it's the tip of that arrow. So now in this coordinate system, we just have to figure out the coordinates of that point. The orientation is saying, where does the tip of the car lie compared to the back of the car? You know what I mean? So you could have the position of that point in the same spot with the car in infinitely many different orientations. It just has to do with where the headlights are facing, you know.
Okay. So if the car was on a hill, like going downward, then the position would be different, but the orientation would be the same?
The orientation would be different. The position, depending on where the hill was, could be the same or different.
Oh, I thought you just meant like what direction the car was.
That's the orientation. That's
Okay.
angular position.
Okay. Thank you.
Sure. The units for angular velocity are radians over time. And so the SI units are radians per second. And just like the particle velocity tells you what direction an object is moving, the angular velocity tells you what direction the object is rotating. So notice, that's okay. So notice that a positive value of the angular velocity means the object is rotating counterclockwise. And a negative value means it's rotating clockwise. An example? Yeah, so if you, well, if a baseball is flying through the air, spinning like this, if you measured its angular velocity, you'd get a positive value. If it was spinning the other way, you'd get a negative value. Yep. Okay, so that's all I want to say about angular velocity. So now angular acceleration. Remember that when we talked about particle acceleration, the acceleration was equal to the velocity at the later instant minus the velocity at the earlier instant divided by the elapsed time. We didn't make a distinction between average acceleration and instantaneous acceleration because all of our accelerations during this time were constant. So it was the same thing. The instantaneous acceleration was the average acceleration. So with that idea, similarly, the angular acceleration is equal to the angular velocity at the later instant minus the angular velocity at the earlier instant divided by the elapsed time. This is a measure, so the particle acceleration was a measure of how quickly the velocity was changing. The angular acceleration is a measure of how quickly the angular velocity is changing. So is the rotation speeding up or is the rotation slowing down? The units for angular acceleration are radians over time squared. And the SI units are radians per second squared. And so based on how similar all of these things, the relationships between these quantities are to the way they were with particles, who wants to make a guess at how you know whether a rotation is speeding up or slowing down? It's not just positive or negative. It depends. It depends on the velocity and the angular velocity and angular acceleration direction. And if they both have the same sign, the rotation is speeding up. And if they both have opposite signs, the rotation is slowing down. Okay? Just like it was with particles. So notice if the angular velocity and angular acceleration have the same sign, the rotation is speeding up. And then if omega, angular velocity and angular acceleration, have opposite signs, the rotation is slowing down. Okay, any questions about those? So you can think of angular position as telling you the orientation of an object at a single instant. Angular velocity is how quickly that orientation is changing. And angular acceleration is how quickly that angular velocity is changing.
And are all of these measurements independent of like 2D kinematics? So it doesn't matter how fast the car is going?
That's right, it's independent. So you could have, excuse me, so you could have, well, think about like a boomerang or a baseball or something. Something can be, the position of some point on the body can be changing at the same time that its orientation is changing. So it's independent, yeah. Okay, so now I'm going to give you a bunch of, well, I'm going to give you ways to go between those particle quantities that represent like the velocity and acceleration of a single point on the body, and these rotational quantities that we just talked about. So these are equations to go back and forth between the rotational quantities and the particle quantities representing a single point. The first one of these goes back and forth between the speed of an individual point and the angular velocity of the body. So the speed of an individual point is equal to the absolute value of the angular velocity times r, and I'll tell you what these are. So this v is the speed. That's the angular velocity. And then this r is the distance from the axis of rotation to the desired point. Yeah, r is for radius. And it's really a distance, but the reason it's given that name r is because every point is moving in a circle. And so if you think of that point as being represented by its circular path, that r is the radius of that circle, the circular path. And then the second equation gives the magnitude of the tangential acceleration. So this is the magnitude of a tangential. and it's equal to the absolute value of the angular acceleration times that same r. So that r is still the distance from the axis of rotation to the point you care about. And so if you have a problem where you have a way to figure out the angular velocity and the angular acceleration, say, and you're asked to calculate like the acceleration, then you use the first equation to find v, use v to calculate the centripetal acceleration, use the second equation to find the tangential acceleration, add those two together to get the total acceleration, and then I guess that's all I asked for. Okay, so let's do an example. All right, so let's say we have that board. And it can spin freely around this pin. So that's the axis of rotation. And let's say the board is rotating counterclockwise with an angular speed of 10 radians per second. And let's say it's slowing down at 5 radians per second squared. And let's say there's another point on this board, I'll call it P, that's 0.3 meters away from the axis. We want to calculate first the velocity vector at P, and second the acceleration vector at P. And like I said, the angular velocity and angular acceleration hold for the whole board, but if I had chosen a different point P, we would get different values for the velocity and acceleration of that point. Okay. All right, so first I'm going to just to make it easier to visualize, I'm going to draw the circular path that this point is following. It looks something like that. And the board's rotating counterclockwise, so the velocity vector, is it up or down? Well, think of it the same way that we did when we were doing circular motion. If it's rotating like this, the velocity vector has to be that way. So down. And is the rotation speeding up or slowing down? It says slowing down. That's how you know. So the velocity is this way. The tangential acceleration's this way. The centripetal acceleration's toward the center of the circle. And now that we have all the directions, we can just worry about the magnitudes and start putting it all together. So first, the velocity vector. How are we going to calculate the velocity vector? Yeah. So the speed is equal to the absolute value of the angular velocity times r. So that's equal to 10 times 0.3. Or 3 meters per second. And so the velocity vector is 3 meters per second down. Or if we have the standard coordinate system, that's in the negative y direction. So that's 0, negative 3. Okay, so now the acceleration. This one takes a couple of steps. Well, first, let's calculate the magnitude of the centripetal acceleration. That's v squared over r, and we know the direction is this way. We already figured that out. The speed is 3, so 3 squared divided by the radius is 0.3. And so you get 30 meters per second squared this way in the positive x direction. So that's 30, 0. Yep. Any questions about the centripetal acceleration? And then the tangential acceleration, we have one of those equations for. The tangential acceleration magnitude is the absolute value of the angular acceleration times r. So that's 5 times 0.3, or 1.5 meters per second squared. And we already figured out the direction of the tangential acceleration is up. So the tangential acceleration vector is 1.5 meters per second squared up, which is 0, 1.5. And then the last step is just adding those two together. The total acceleration is 30, 0, plus 0, 1.5. So 30, 1.5, and the units are meters per second squared. Any questions about that?
Are you always going to be asking for the vector?
Yeah, you should be able to do that. I mean, there are times that I won't, but you should be ready for that, yeah. Any other questions? Okay, so here's the last thing we're going to do with kinematics. There are 3 more equations. They look just like equations you've seen before. So the last 3 equations in rotational kinematics are the constant angular acceleration equations. There are 3 of these. They look just like the particle versions that we've dealt with. So the first one says angular velocity final is equal to, what do you think? Angular velocity initial plus angular acceleration times time final. Yep. So that's the equivalent of, VF is equal to VI plus ATF. And then we have the second one, the one we're used to says PF is equal to PI plus blah, blah, blah. So this one says angular position final is equal to angular position initial plus angular velocity initial times time final plus 1/2 angular acceleration times time final squared. And then the last one says 2 times alpha times the quantity theta final minus theta initial is equal to omega final squared minus omega initial squared. And to use these, it's the exact same approach as it was for particle stuff. You just need to make sure that you know enough of these variable values so that one of these equations only has one unknown, just like it was with particles. So let me do an example. Okay, so let's say that a centrifuge with a radius of 0.1 meters accelerates from rest to 2,000 RPM in 1 second. I don't know, is that possible? Who knows? Impossible to know. And we want to know first what's the angular acceleration, and second, what's the acceleration vector of a particle on the outside at the outer edge of the centrifuge. So this acceleration that we're going to calculate in part B tells you, how effective this centrifuge is going to be at separating things, or whatever centrifuges do. They separate things, right? All right, so to figure out the angular acceleration, we can use the equation that says angular velocity final is equal to angular velocity initial plus angular acceleration times time final. I have to convert 2,000 RPM into radians per second first. So 2,000 rotations per minute one rotation, how many radians is one rotation? 2 pi. And 1 minute is 60 seconds. And so that gives 209.44 radians per second. And now we can plug everything into this equation. Omega final is 209.44. It's starting at rest, so omega initial is 0, plus alpha times, it's doing this over an interval of 1 second. And so alpha is 209.44 radians per second squared. Any questions about that part? Okay, so now the rest of this problem is basically like the last example problem we did. It didn't say anything about the direction or the point that this particle is at the instant we're looking at, so we can choose whatever we want for those. The circular path is like this. Let's say that it's going counterclockwise. That's usually easier because your numbers, your values are positive. That's right, yep. And let's choose, I don't know, let's choose this point over here. Okay, so if it's going this way, we know the velocity vector is going to be down. Is it speeding up or slowing down? Speeding up, so tangential acceleration is also down. That it's speeding up. It went from rest to this really high speed, so it's speeding up. And then the centripetal is towards the center. And now we can just go through these one by one just like we did before. The speed is equal to omega times r, absolute value. Omega was 209.44. The radius was 0.1. And so the speed is 20.94, I guess I'll keep the other 4, meters per second. It didn't ask for a velocity vector, but if we wanted the velocity vector, it's in the negative y direction. So the velocity vector would be 0, negative 20.944. But what we want is the acceleration. So first, the centripetal acceleration is going this way towards the center, and it has a magnitude of v squared over r. So that's 20.944 squared divided by 0.1. Can someone multiply that? 4386.5. And that's meters per second squared to the right, and that's in the positive x direction, so 4386.5 for x, 0 for y. And now the tangential acceleration. We already know that that's pointing down. And we're going to calculate that as angular acceleration times r. So that's down. Angular acceleration was 209.44 multiplied by 0.1. So we get a vector of 0, negative 20.944. Yes?
I thought we calculated as a quantity control, not 29.
The angular acceleration we calculated up here was 209. The velocity here was 20.944. But to calculate the acceleration, we need to multiply the angular acceleration times the radius. And so now the total acceleration is, add those two together, you get 4386.5, negative 20.944 in meters per second squared. And so that's something like 500 Gs, a huge acceleration, which is what you need to, to use this to separate out things of different masses. Any other questions about this? Okay, so there are practice problems for rotational kinematics. There aren't very many of them. I think there's only like 3 or 4, and you can do all of those now. And then on Thursday, we'll do rotational kinetics, and then we're done. Okay.